Now let us see how any vector is converted from Cartesian to spherical, or vice versa, from spherical to Cartesian. And for that, you must know the relation between their unit vectors. Am I right? My dear, you know that in Cartesian coordinate system, any vector is represented using unit vectors ax, ay and az. While spherical coordinate system, it is characterized by unit vectors ar, a theta and a phi. So if I want to convert between these coordinate systems, then I must know what are the relations for their unit vectors. Am I right? So let us try to find the relations for unit vectors of Cartesian and spherical coordinate system. For simplicity, let us try to find the expressions for Cartesian unit vectors in terms of spherical unit vectors. That means let us assume that we are already given with spherical unit vectors ar, a theta and a phi, and we will try to find the expressions for ax, ay and az in their terms. But before moving ahead, let us properly visualize these unit vectors. Let us assume that we are given any point P in the space as like this, represented in the spherical coordinate system. Now, my dear, in the lecture of vector representation, we have defined each and every unit vector. We have seen that how any unit vector can be drawn. Unit vector AR, it is normal or perpendicular to R equal to constant plane in the increasing direction of R, as like this. Unit vector A theta, it is normal to theta equal to constant plane in the increasing direction of theta. Am I right? As like this. And unit vector A phi, it is exactly the same as we have seen in the cylindrical. Normal to phi equal to constant plane in the increasing phi direction. So these are the three mutually perpendicular unit vectors of the spherical coordinate system. You can clearly see from the figure. AR, A theta and A phi. Isn't it? So these are three mutually perpendicular unit vectors of spherical coordinate system at any random point P. And now we have to find their total equivalent along the positive x-axis, positive y-axis and positive z-axis to get the expressions for unit vectors ax, ay and az. Isn't it? So first of all, consider the unit vector AR. Let us find its components along x, y and z axis. Now my dear, this is exactly the same as we have just seen in the conversion of a point from spherical to Cartesian. We can decompose unit vector AR into AR cos theta along z axis and AR sin theta in the xy plane. And again we can decompose this AR sin theta along x and along y, as you can see from the figure. So these are the components of unit vector AR along x, y and z axis. Now let us consider unit vector A theta. Unit vector A theta is perpendicular or normal to theta equal to constant surface. Isn't it? So look carefully from the diagram. This unit vector A theta is making an angle of 90 minus theta with the minus z axis. Again I am repeating, this unit vector A theta is making an angle of 90 minus theta with the negative z axis. Look carefully in the diagram. So we can decompose its two components, one along minus z axis and another in the xy plane, making an angle phi with the positive x axis, as you can see from the figure. And again we can decompose this A theta cos theta into its two components along x and y axis. So these are the final three components of unit vector A theta along x, y and z axis. And my dear, the components of unit vector A phi we have already seen in the last lecture of Cartesian cylindrical conversion. A phi sin phi along minus x axis and A phi cos phi along plus y axis. Isn't it? Now let us connect all the components of unit vectors AR, A theta and A phi into a single diagram. So now from this diagram, we can easily find the resultant x component, resultant y component and z component of all these unit vectors er, e theta and a. In other words, from this diagram, we can easily find the expressions for Cartesian unit vectors ax, ay and az in terms of spherical unit vectors ar, a theta and a phi. You can easily check out the diagram. And my dear, working on the similar lines, you can easily find the expressions for unit vectors ar, a theta and a phi in terms of ax, ay and az. Now let us assume that we are given with a vector represented in the Cartesian coordinate system, but we wish to represent the same vector into the spherical coordinate system. You also know that in Cartesian coordinate system, the standard form of representing the vector is like this. In Cartesian coordinate system, vector is characterized by unit vectors ax, ay and az. But while representing the same vector in spherical, we will need the unit vectors ar, a theta and a phi, isn't it? So my dear, we have just seen the expressions for Cartesian unit vectors in terms of spherical unit vectors. So let us put these into expression. We will get like this. We can easily collect the terms and arrange the terms, and we will get the same vector as like this in terms of unit vectors ar, a theta and a phi. So this is the same vector but represented in the spherical coordinate system. You also know that in spherical coordinate system, the standard form for representing any vector is like this. It consists of r component, theta component and phi component. So we can also say like this. R component is given as like this. Theta and phi components are given as like this. So these are the conversion formulas for converting any vector from Cartesian to the spherical coordinate system. My dear, we are converting the given vector from Cartesian coordinate system. That means we already know the x component, y component and z component, capital X, capital A and capital Az. And as we want to represent it into the spherical, we will be needing r component, theta component and phi component. So these are the formulas that we should use while converting a vector from Cartesian to spherical. And as we have discussed in the Cartesian cylindrical lecture, these formulas can be easily assembled into the matrix form as like this. So we should remember this matrix formula for converting any vector from Cartesian to spherical. Again I am repeating, we are converting from Cartesian to spherical. That means we already know x, y and z components, but we will find r, theta and phi components. And now my dear, what will be the formula if we are converting the vector from spherical to Cartesian? Converting from spherical to Cartesian, that means we already know the r, theta and phi components, but we want to find x, y and z components. In such case, you can go in the similar process and we can find the matrix formula for that conversion. But my dear, as we have seen in the previous lectures, the formula for that conversion, the matrix for that conversion will be exactly the transpose of this matrix, isn't it? So for converting the given vector from spherical to Cartesian, our required matrix formula will be like this. So this is the formula for converting from Cartesian to spherical, and this formula will be used for converting any vector from spherical coordinate system to the Cartesian coordinate system. In spherical coordinate system, the vector components are ar, a theta and a phi. In Cartesian coordinate system, the components are x component, ax, ay and az. So according to the question, you can use one of these formulas. So these are the formulas for converting any vector from Cartesian to spherical or from spherical to Cartesian. Let us solve a numerical. You can read the question from your screen. The given vector is in Cartesian coordinate system. Check out its unit vectors ax, ay. and we are asked to represent the same vector into the spherical coordinate system. So as given vector is in Cartesian coordinate system, let us compare it with its standard form. We can easily get capital AX, capital AY, that means X component, Y component and Z component, like this. And my dear, we have just discussed the formula for converting from Cartesian representation to the spherical one. Given vector is in Cartesian, that means we already have X, Y and Z components, but we want to represent it in the spherical coordinate system. That means we want r, theta and phi components. So doing simple matrix multiplication, we can easily get r, theta and phi components, and in standard way it is represented as like this. So the given vector A vector in Cartesian is represented in spherical coordinate system, as you can see from the screen. But can you notice there is one problem? Check out our last step. My dear, we are asked to represent the given vector into spherical coordinate system. Spherical coordinate system is characterized by coordinate variables r, theta and phi, unit vectors ar, a theta and a phi. So check out our last step. Unit vectors are okay, but the last step still consists of Cartesian coordinate variables. You can still find their x, y and z. So you know, my dear, we have to convert those Cartesian x, y and z variables into their equivalent spherical coordinate variables, that are r, theta and phi. And as we have discussed in the initial part of this lecture, the conversion formulas for x, y and z in terms of spherical coordinates are like this. So we can easily put these expressions into our last step and we can easily conclude to our final answer for representing the given vector into the spherical coordinate system, as you can see from the screen. So we have seen how to convert any point or any vector from Cartesian to cylindrical, or back from cylindrical to Cartesian. We have also seen the Cartesian spherical conversion, or vice versa spherical to Cartesian conversion. So the last remaining case is cylindrical spherical conversion. But we would not go for it, because you know, it will be just piling up the unnecessary formulas. Because consider, well, say for example, you are given with a point or vector in cylindrical coordinate system and you want to represent the same point or vector into spherical coordinate system. Then my dear, you can do it into two steps. In step number 1, you can convert that given point or vector from cylindrical into Cartesian, and in step number 2, you can convert from Cartesian to get the answer into spherical. So rather than memorizing complete new set of formulas, this two-step process will be very much easier, isn't it? So we would not go for cylindrical spherical conversion, but we will go like this.